Hi ladies and gentlemen, in this video we discuss the correlation receiver. So this is based on this receiver works based on the Gram-Schmidt procedure. So let me start with that presentation. So the speech is organized into your learning outcomes, the structure of the correlation receiver and its demo in Python, and summary of understanding. So you will learn the operation of a correlation receiver in this video, and then you will observe the demo of correlation receiver and appreciate the bit error rate signal to noise ratio curve. Now what happens is, in the baseband transmission you transmit the bits by passing it through a transmitter filter. Say I have a transmitter filter with impulse response, say ST. It can be either S plus ST or minus ST, depending on whether the bit is a 1 or a minus 1. So we convolve the bits with a transmitter filter ST, and then the resultant thing is the bit stream is BT, so it is ST convolution BT, and it is transmitted through the additive white Gaussian noise channel that adds a noise NT. So that RT is equal to ST convolution BT plus NT. Now at the receiver, I have a copy of this ST, whatever signal, transmitted impulse response, I have a copy in the receiver. All I do not know is whether I get ST or minus ST at a given instant. So here it is multiplied with ST, so that and then it is integrated over one bit duration, that is 0 to t. So this thing together, this is equivalent to a dot product. So depending on whether the input bits are plus or minus 1 ST or minus ST is transmitted at the receiver, this is multiplied by ST, so that and then it is integrated to yield a single value. So if the single value is at here, if it is greater than 0, a decision that bit 1 is transmitted, that is made. If it is less than 0, I say bit minus 1 is transmitted. So the probability of error will be q d by 2 sigma. So we have half error function complement d by 2 root 2 sigma, because we know that q of x is half error function complement x by root 2. Now this d by 2 is the signal strength. Okay, this d by 2 is a signal strength because I have two signals, ST or minus ST, separated by d. So d by 2 is one signal value. So this is nothing but the and this sigma, this is the my noise my noise standard deviation. So this d square by 4 divided by sigma square, that is my signal to noise ratio. So I can say that this is root of SNR by half error function complement root of SNR by 2. So this equation I can demonstrate with Python. So here is a Python code for the correlation receiver. First I import the two modules SciPy and PYLab, then I transmit 1000 bits. So then I define a time variable that is 0 to 1 with an increment of 0.1, and I take my signal ST as a once for the duration that is equal to the length of t, and the symbol interval is nothing but the length of t. Then I transmit plus or minus random bits of plus 1 and minus 1. So I just assign random gives me random numbers between 0 and 1. When I subtract 0.5 from it, it becomes some of them randomly become positive, some of them become negative. So I take the sign of that one. So it is I get a random bit stream. So B is nothing but a random bits stream of plus or minus 1. So I use a transmitter, I initialize a transmitter bit array here, and for 0 to 1000, if BI is 1, if the bit is 1, I append ST to the transmit bit array, and else I append a negative of ST. So this transmits, I concatenate this this array so that I get my transmitted bits. Okay, it is nothing but plus or minus st, sequence of plus or minus st. And the receiver I initialize a blank array. Then in this two lines I implement a correlation receiver. So I multiply this transmitted bits by the symbol transmitted bits by st. If it is greater than 0, then instead of the integration I do a summation over one symbol interval. So this is one symbol. When I equal to 0, it is 0 to one symbol interval. So this is iterated over I. So if this sum is greater than 0, then the receive bits are appended with 1, or else the receive bits are appended with zeros. Now so I can run this code. Python 3. Now you can see that the code runs without any problem. Now if you compare the transmitted bits with the received bits, you can see that they are the same. If I say the trans bits here, if I type the trans bits here, you can see that it's a array of 1 or minus 1, or rather I will say, instead of the transmitted bits, I will say B. It is a binary sequence, so you have a random binary sequence. Now if you see the received bits, you can have an identical sequence here. Now you can compare these two things, and you can see that all these values are, or this difference, if I take the difference between received bits and B, you can see that all of them are zeros, because they are equal. Received bits are the same as the transmitted bits, and if I take the sum of this array, you can see that it is 0, because everywhere the received bit is equal to the transmitted bit. Okay, now this correlation receiver works very well. Now we have to see what happens when there is noise in the channel. Now here I have a system here. I have a new code here. What I do is like in the previous code, I import SciPy and PyLab. Of course, I import the SciPy.special library as SP. This I use for computing my what is nothing but the Q function or the error function. So here also I transmit some 5000 bits. I make a transmitted bit array, and instead of directly transmitting, I transmit through an AWN channel. So I assume that the noise level is from minus 40 dB to 10 dB with an increment of 2. I compute the noise variance from this, and the energy per bit, that is the length of ST, because all are ones. ST contains a sequence of ones, and SNR is computed this way, EB by noise variance, and SNR dB is computed, and I initialize a bit error rate array. Then for different noise variances, you create a noise that is square root of j, that is root of j will be the magnitude of the noise, because it's a noise variance. And random alien transmit means random gives me a Gaussian random variable. So the transmitted bits are added to noise to get the received signal, and I initialize a receive bits array here, and here for all values of I from 0 to 5000, I compute this thing. I create a correlation receiver here, and if this dot product is greater than 0, then the receive bits are appended with 1, or else the receive bits are appended with zeros. Then I compute the BER value. I take the difference between B and receive bits, as in the last case. We take the difference between B and receive bits and take the absolute value of difference and sum it up and divide by n, so that this is the number of bits made in the bit pattern, number of bits in error. Now BER array is appended with a BER val. Then the theoretical value is computed this way. From the last equation I compute 0.5 into error function complement root of SNR by 2. Then I plot these transmitted bits as well as the theoretical BER and the actual bit error rate against the signal to noise ratio. So let us run this code and appreciate this. Now this is my transmitted signal. This is plus ST or minus ST is transmitted for bit 1 or minus 1. Here you can appreciate this. It's a random stream, rectangular pulses. If the bit is a 1, I send a positive rectangular pulse. If the bit is a negative 1, I transmit a minus ST. So this is how the bit part, the transmitted signal look like. Now here you can appreciate the bit error rate SNR curve. So this dotted curve is a theoretical curve, that is half error function complement root of SNR by 2, and this is this red curve, this wiggly curve, this is the bit error rate on transmission. That is the practical one, the experimental one, that is a red curve, and this blue dotted curve, that is a theoretical curve, that is half error function complement root of SNR by 2. Now we see that the theoretical model that is validated by experiment or simulation. Now let me go back to my presentation. So this is the BER-SNR plot. Now coming to the end, in this video you understood the operation of correlation receiver and observed the demo using Python. Then you appreciated the BER-SNR plot of the correlation receiver, and that is the end of this presentation. I thank you all.